You could build chips that are perfectly suited for just one kind of AI model. But if you do that, then you're making them less able to do other things. So as these specific structures or architectures of AI get more popular, my understanding is there's a debate between how much you place these bets on burning them into the chip or designing hardware that is very specific to a certain task versus staying more general. And so my question is, how do you make those bets? How do you think about whether the solution is a car that could go anywhere or it's really optimizing a train to go from A to B? You're making bets with huge stakes, and I'm curious how you think about that.
Yeah, and that now comes back to exactly your question: what are your core beliefs? And the question, the core belief, either one, that transformer is the last AI algorithm, AI architecture that any researcher will ever discover again, or that transformers is a stepping stone towards evolutions of transformers that are barely recognizable as a transformer years from now. And we believe the latter. And the reason for that is because you just have to go back in history and ask yourself, in the world of computer algorithms, in the world of software, in the world of engineering and innovation, has one idea stayed along that long? And the answer is no. And so that's kind of the beauty. That's in fact the essential beauty of a computer, that it's able to do something today that no one even imagined possible 10 years ago. And if you would have turned that computer 10 years ago into a microwave, then why would the applications keep coming? And so we believe in the richness of innovation and the richness of invention, and we want to create an architecture that let inventors and innovators and software programmers and AI researchers swim in the soup and come up with some amazing ideas. Look at transformers. The fundamental characteristic of a transformer is this idea called attention mechanism. And it basically says the transformer is going to understand the meaning and the relevance of every single word with every other word. So if you had 10 words, it has to figure out the relationship across 10 of them. But if you have 100,000 words, or if your context is now as large as read a PDF and read a whole bunch of PDFs, and the context window is now like 1 million tokens, processing all of it across all of it is just impossible. And so the way you solve that problem is there are all kinds of new ideas, and flash attention or hierarchical attention, or all the wave attention I just read about the other day. The number of different types of attention mechanisms that have been invented since the transformer is quite extraordinary. And so I think that that's going to continue, and we believe it's going to continue, and that computer science hasn't ended, and that AI research has not all given up, and we haven't given up anyhow, and that having a computer that enables the flexibility of research and innovation and new ideas is fundamentally the most important thing.
One of the things that I am just so curious about, you design the chips. There are companies that assemble the chips. There are companies that design hardware to make it possible to work at nanometer scale. When you're designing tools like this, how do you think about design in the context of what's physically possible right now to make? What are the things that you're thinking about with sort of pushing that limit today?
The way we do it is, even though we have things made, like for example, our chips are made by TSMC. Even though we have them made by TSMC, we assume that we need to have the deep expertise that TSMC has. And so we have people in our company who are incredibly good at semiconductor physics, so that we have a feeling for, we have an intuition for what are the limits of what today's semiconductor physics can do. And then we work very closely with them to discover the limits, because we're trying to push the limits. And so we'll discover the limits together. We do the same thing in system engineering cooling systems. It turns out plumbing is really important to us because of liquid cooling, and maybe fans are really important to us because of air cooling. And we're trying to design these fans in a way almost like, they're aerodynamically sound so that we could pass the highest volume of air, make the least amount of noise. So we have aerodynamics engineers in our company. And so even though we don't make them, we design them, and we have the deep expertise of knowing how to have them made, and from that we try to push the limits.
One of the themes of this conversation is that you are a person who makes big bets on the future, and time again you've been right about those bets. We've talked about GPUs, we've talked about CUDA, we've talked about bets you've made in AI.
Self-driving cars, and we're going to be right on robotics. And
this is my question.
Yeah,
what are the bets that you're making now? We're going to be right on Omniverse.
The latest bet, of course, we just described at the CES, and I'm very, very proud of it, and I'm very excited about it, is the fusion of Omniverse and Cosmos, so that we have this new type of generative world generation system, this multiverse generation system. I think that's going to be profoundly important in the future of robotics and physical systems. Of course, the work that we're doing with humanoid robots, developing the tooling systems and the training systems and the human demonstration systems and all of this stuff that you've already mentioned, we're just seeing the beginnings of that work. And I think the next 5 years are going to be very interesting in the world of humanoid robotics. Of course, the work that we're doing in digital biology, so that we can understand the language of molecules and understand the language of cells, and just as we understand the language of physics and the physical world, we'd like to understand the language of the human body and understand the language of biology. And so if we can learn that and we can predict it, then all of a sudden our ability to have a digital twin of the human is plausible. And so I'm very excited about that work. I love the work that we're doing in climate science, and be able to, from weather predictions, understand and predict the high resolution regional climates, the weather patterns within a kilometer above your head, that we can somehow predict that with great accuracy. Its implications is really quite profound. And so the number of things that we're working on is really cool.